Generalized approximation spaces arise from the theory of rough sets, which was introduced in 1982 by a Polish scientist Zdzisław Pawlak. And rough sets, they are used to model uncertainty, but in a manner different than the one that is used in case of, let's say, fuzzy sets, vague sets, or intuitionistic fuzzy sets, or soft sets. There are many approaches, and one of them is the theory of rough sets. Well, shortly speaking, while rough sets deal with approximation spaces founded on equivalence relations, in case of generalized approximation spaces, we may use any binary relations. Now, this presentation is based on two papers. One is by Sheeja and Kuriakose. This is continuity on approximation spaces. And one is by Pei, and Zhen. This is topology versus generalized rough sets. A vast majority of definitions, notions, symbols, theorems, and examples is taken from the first paper, even if some of them, or maybe even many of them, have been proved earlier in this paper or in other papers which are or which are not in our bibliography at the end of this presentation. Now let us define generalized approximation space. This is just an ordered pair x theta, where theta is an arbitrary binary relation on non-empty universe X. And here we define something similar to the concept of equivalence class, but of course we remember that theta need not to be equivalence. So theta of u is just a set of these elements, this v, such that u and v are connected by the relation theta. Now we define the lower and upper approximations of A contained in X. A is a set contained in our universe, and we define its lower and upper approximation with respect to theta. And this idea is taken from Pawlak, from his theory of rough sets, but here it's extended to any binary relations. Here we have lower approximation. This is the set of all those elements u such that theta of u is strictly contained, well, not necessarily strictly, but is contained in A. And here we have upper approximation, underline A. This is the set of all those elements for which their theta class has non-empty intersection with A. Now let us recall the basic properties of binary relations. We assume that they are well known: connectedness, reflexivity, symmetry, transitivity. Moreover, we have these two notions, quasi-order or pre-order. It means that our relation is reflexive and transitive, and equivalence, reflexivity, symmetry, and transitivity. Well, going back to generalized approximation spaces, we may prove some basic properties. Among them, there are all these properties and many other, of course. But we choose these 6 properties. Now, as you can see, lower approximation of the whole universe is identical with the whole universe. Upper approximation of empty set is empty set. And here are some relationships referring to the intersection and union of sets and their approximations. You may prove them, or you may find proofs in our bibliography. Moreover, we have these properties. This one is important, that lower approximation is contained in A, and A is contained in its upper approximation, even only if theta is reflexive. And this property is very important, and in fact, later we shall deal mostly with reflexive approximation spaces. What about topology? Kondo proved that if theta is reflexive, just as we said, then this set, tau theta, the set of all those A contained in X such that their lower approximation is identical with them, is a topology on X. And this is so-called induced topology on X theta. However, the fact that theta defines certain topology does not mean that theta is reflexive. So there is no equivalence here. It has meta-equivalence. Now, for example, for this universe, PQRS, and for this relation theta, we have this set tau theta, and one can prove that this is topology, but this relation theta is not reflexive. Hence, we should find a necessary and sufficient condition for theta to form a tau theta topology on X. And our authors prove that tau theta is a topology if and only if tau is connected, or as you prefer this notion, serial. All these properties, which are here below, namely 1, 2, 3, they should be preceded by the following assumption, following statement. If X theta is a reflexive approximation space, then this, or this, and finished by if and only if theta is transitive. So on the right side of each of these statements, you have meta-equivalence if and only if theta is transitive. So for example, if and only if theta is transitive, lower approximation of A is identical with the union of all theta of A such that theta of A is contained in A. Another theorem refers to the notion of upper approximation. And upper approximation of A is identical with the union of all theta of A such that theta of A and A have non-empty intersection, but this is this equality holds if and only if theta is an equivalence relation. So here we have weaker condition when compared to this one, but here we have stronger condition. Yes, equivalence, not only transitivity, as it was here. The next theorem deals with the question of discrete topology, the one in which each subset is open. If X theta is reflexive approximation space, then tau theta is the discrete topology on X if and only if theta is, yes, this relation. One can also prove that if theta I is equal to the whole Cartesian product of X with itself, then tau theta I is the indiscrete topology, so only empty set and the whole X are open. However, authors prove that indiscrete topology can also be obtained by other reflexive relations, not only by this one. These were only initial informations about generalized approximation spaces. What is interesting is the fact that our authors analyzed the notion of continuity in this setting, in this framework. As we remember, if we have two topological spaces, one with tau and one with universe x prime and tau prime topology, then a function f from x to x prime is called continuous if the inverse image of every tau prime open set is tau open. And the next theorem proved by our authors refers to quasi-ordered approximation spaces, quasi-ordered. If we have two spaces of this kind, then the function g is continuous if and only if the following holds, that from the fact that u and v are in relation tau, we may infer that their values g of u and g of v are in relation tau prime for all uv in X. There are also other theorems, among them this one. Assume that we have two quasi-ordered approximation spaces and certain function between them, which is bijection, function g. And then the following statements are equivalent. G is homeomorphism, that is both g and inverse g are continuous with respect to tau and respectively tau prime. And then this is equivalent with these two conditions. For example, in this case, it means that the image of upper approximation of A by function g is equal with upper approximation of g of A with respect to tau prime here, and that holds for any A containing X. And here we have analogous sentence for lower approximation. This is our bibliography. Of course, there are many other papers about these topics. Thank you very much for your attention.